In this set of notes, we're going to look at how to find derivatives of exponential functions. So to start with, as a reminder, we call f of x an exponential function with base a if f of x takes the following format. And so notice we have a constant to the power of x. Now, there are other ways that we could write exponential functions. It doesn't just have to be a single x. So for example, we could have a function of x, so maybe we would have 3 to the x squared plus x, for example, would be another example of an exponential function where we have a base of 3. But the important part with exponential functions is that we do have x, or whatever variable we're looking at a function of, in the exponent. And then the derivative of these functions is given by the following. And so notice here we are assuming that we only have the a in the exponent. We'll look at an example later on where we have a function of x in the exponent, and we'll be able to see we can use this same derivative rule. We'll just need to also apply the chain rule. So your book gives a discussion of how to find the derivative. Please read this on your own. And in that discussion, they introduce the definition of base e in derivatives. It ends up that base e in the derivatives is commonly used in probability. So even though you won't see the utility of it in this course, do know that this information is very important, and you'll kind of want to star this, or make a note, come back to here, because once you get into BST 675, this you'll want to come back and review this material, because we will use base e and exponential functions quite a bit in that course. But as you'll see in this chapter, taking derivatives of exponential functions really isn't too bad, especially when we're working in base e. So here's the definition of base e. It ends up that base e is the only base for when we take the limit of e to the h minus 1 over h, it's equal to 1. And you'll read in the book more about why this limit is important, but you should recognize this limit as being the form of a limit whenever we look at taking derivatives. And so it ends up that we get two important results that, again, you'll use a bunch in BST 675, and they are the following. It ends up that the derivative of e to the x is equal to e to the x. And then the next box is actually just an application of the chain rule, and it says that if you have the derivative of e to a function of x, that is equal to the derivative of the function times e to gx. And so again, this is just a direct application of the chain rule, that second box. And so one thing to note is that when we write f of x is equal to e to the x, that can also be written as f of x is equal to exp x. And so here, this is the exponent function or exponential function. The reason that the second one is useful is there are times when maybe, we don't just have x in the exponent, but again, we have a function of x. So let's say we had something like g of x is equal to e to the 3x cubed plus 2x squared plus 6. When we get to where we've got, pretty long functions in the exponent, especially when we're writing these by hand, if our handwriting isn't really clear, it may be hard to distinguish this from, let's say, e to the 3x squared plus 2x squared plus 6. And so notice, in the first case, the function we actually want, all of this is in the exponent, whereas in the second one, only this piece is in the exponent. So just using handwriting, it can get a little sloppy if we're not really careful to make sure everything's elevated. And so that's one reason that instead, when we have that, bigger function in the exponent, we'll write this as exp 3x cubed plus 2x squared plus 6. So that way it's just clear that that entire function is in the exponent. And so again, that's a notation. Your book uses it a little bit, but later on, especially in probability courses, that second way is used a lot. just to make it clear, that that entire function is in the exponent. All right, so let's look at a couple different examples. We're going to start out by looking at some examples where we are working with base e, and then we'll look at an example where we're working with a base different than base e. All right, so for this first example, we have f of x is equal to e to the negative 2x. So notice here that in the exponent we do have a function of x. We've got negative 2x. So we're going to want to apply the chain rule. Or we're really just applying this second box right here. So here f prime of x is equal to, well, we're going to have e to the negative 2x, because we know that the derivative of e to the x is equal to e to the x, but negative 2x is what we would call the inner function in the chain rule, so we also have to multiply by its derivative, and the derivative of negative 2x is equal to negative 2. Now, similar for reasons that when we worked with the trigonomic function, we will pull that negative 2 out front, and so we end up with negative 2e to the negative 2x. All right, so let's look at another example. So notice in this example, we have a function of x multiplied by a second function of x. That second function is e to the 1 minus x squared. So notice here we know that we're going to need to use the product rule. Because we have those two functions multiply by one another, and we're also going to need to use the chain rule because we have e to a function of x. Right, so we've got f prime of x, so we're going to apply that chain rule. So the first thing we're going to do is we're going to multiply our first function by the derivative of the second function. Well, notice to take the derivative of the second function, that's where we're going to need the chain rule. So we're going to have e to the 1 minus x squared, because again the derivative of e to the x is e to the x, but since we have a function in the exponent, we need to also multiply by the derivative of that function, and the derivative of 1 minus x squared with respect to x is minus 2x. And then to complete the chain rule, so here we had the first function multiplied by the derivative of the second. Then we're going to have the derivative of the first function, which is going to be 6x, multiplied by the second function. So as usual, we want to simplify this. Notice that both of the terms here involve an e to the 1 minus x squared. So I'm going to pull that out, and I'm actually going to write it using that other notation, the exp to the 1 minus x squared. And that is going to be multiplied by 3x squared minus 1 times negative 2x plus 6x. And then I'm going to simplify the inside of those brackets. I'm going to have negative 6x cubed plus 2x plus 6x. Notice that 2x and 6x are going to add together, and I want to pull them in front of the exponent function. So I'm going to end up here with negative 6x cubed plus 8x multiplied by e to the 1 minus x squared. So let's look at some more examples here. Notice here we have a quotient, so we know that we're going to have to use the quotient. And then here in this term, in the denominator right here, notice that we don't have e to the x, we have e to the negative x, and so that is a function of x, so we know we're also going to have to apply that chain rule again. And so here we have by the quotient and the chain rule, we know that f prime of x is equal to, so our two functions are x, which is in the numerator, and in the denominator we have e to the x plus e to the minus x. So to apply the quotient rule, we're going to take the derivative of the first function with respect to x. Well, the derivative of x with respect to x is just 1, times the function in the denominator, minus the function in the numerator, times the derivative of the function in the denominator. Well, here we have the sum of two functions, so we know that's equal to the sum of the derivatives. So the derivative of e to the x is just e to the x, plus we need to take the derivative of e to the minus x. Well, here we have e to the minus x. The derivative of that is just e to the minus x, but we need to also multiply by the derivative of minus x, and so that's just minus 1. And then we need to divide by the function in the denominator squared. And then as always, we want to try to simplify this as much as we can. So in the numerator, we have e to the x plus e to the minus x times e to the x. Oops, and that's going to end up being a minus times a minus, so that is a plus e to the minus x. Again, all divided by e to the x plus e to the minus x squared. Now I am going to group these terms in the numerator. Oops, I just realized I forgot an x right here, because when I multiply negative x times e to the minus x minus 1, I get plus x e to the minus x. So the terms in the numerator, I'm going to group them by the e to the minus x, and I'm going to group them by the e to the x terms. So notice in the numerator, I'm going to have, if I look at the e to the x terms, I'm going to have e to the x minus x e to the x. So that's the same thing as 1 minus x e to the x. And then the e to the minus x terms, I've got an e to the minus x plus x e to the minus x. So plus 1 plus e to the minus x. And then of course that's all over e to the x plus e to the minus x squared. Alright, so those were all examples where we were working with base e. So to finish out here, let's look at an example where we don't have base e. So here we want to find the derivative of f of x, where we have 3 to the x plus 1. So notice for this case, we have base 3, and also in the exponent, we have a function of x. We have the square root of x plus 1. So to make this a little bit easier to work with, I'm actually going to rewrite this as 3 to the x plus 1 to the 1/2 power. That's going to make it easier for us to apply our power rule. And then also here, since we're not working with base e, we're going to want to go back to the first page. And remember, at the very first page, we had this rule for finding derivatives when we were not working with base e. So to find our derivative, we're going to have f prime of x is equal to, well again, we're going to use the fact, I'm going to make myself just a little note here off to the side. We are going to use the fact that the derivative with respect to x of a to the x is equal to the natural log of a times a to the x. So here, our a is equal to 3, and we don't just have x, we have a function of x. So this derivative is going to be equal to the natural log of 3 times 3 to the x plus 1 to the 1/2, but since we have a function in the exponent, sorry, I'm just going to move that so it doesn't get in our way. Since we have a function of x in the exponent, we also need to multiply by the derivative of what's in the exponent. So taking the derivative of what's in the exponent, using the power rule, we have 1/2 times x plus 1 to the negative 1/2, and then multiply by the derivative of what is inside of that function by 1. So really, notice here, we're also using the chain rule. So simplifying this, we're going to have the natural log of 3. We have a 1/2 here, so we have a 2 in the denominator. We also have an x plus 1 to the 1/2 in the denominator, or we could say the square root of x plus 1 multiplied by 3 to the square root of x plus 1. All right, so as usual, if you have any questions or need any help, please let me know.